Okay, in this video we'll be going through the 2017 Scholarship Physics exam. Question 1. The graph shows a theoretical sound frequency of a plane flying by an observation point P against the distance of the plane from the observation point. The plane is emitting a sound frequency of 1000 Hz and has a constant speed relative to the ground. Explain the physical process that causes the change in frequency. State any assumptions that are implied by the shape of the graph. Okay, so this is our regular level 3 Doppler situation. The assumption made by the shape of the graph, as the graph takes a very sharp turn down and back across, that implies that the plane is going straight through the observer, which obviously in a real scenario won't ever happen, otherwise the person will die. So in a real scenario, the graph will probably look something like this. It will be gradually decaying with the true frequency in the middle right there, and then our lower frequency as it goes away. So we can write that in. This is the Doppler effect. As the plane moves, it catches up to previously emitted wavefronts before emitting subsequent wavefronts. Thus, the wavefronts in front of the plane are more bunched up, and the wavefronts behind the plane are more spread out. So essentially, the wavefronts will look something like this. Right? Therefore, as the plane approaches point P, the observer will perceive shorter wavelengths. Thus, as the speed of sound is constant, the observer will hear a higher frequency, and that is this section right here. However, as the plane moves away from the observer will perceive longer wavefronts and therefore hear a lower frequency. Right? And that's that part right there. Again, assuming the speed of sound is constant. Now, as discussed previously, this all assumes that the plane goes straight through point P, which again will not happen. This is the more likely scenario to happen. Show that the plane's speed is 113 meters per second. Okay, so we know our Doppler equation is equal to the frequency of the source times the velocity of the wave all over the velocity of the wave plus or minus the velocity of the source. Now for this calculation, I'm going to be using the plus scenario just to make the math a little bit easier. So this is when the plane is moving away from the observer. So for when the plane is moving away from the observer, our perceived frequency is equal to 750 Hz. So 750 is equal to the source frequency, and that is 1000 Hz, as stated above, times the velocity of the wave, which is the speed of sound, which is 340 meters per second. And that's all over 340 plus Vs, which is the variable that we're trying to find. So now rearranging, we get 340 plus Vs is equal to 1000 times 340 all over 750. Now minusing 340 on this side, and we get the source velocity is equal to 1000 times 340 all over 750 minus 340. And that gives us a source velocity of 113 meters per second, just as we are meant to find. The plane flies with a constant speed of 113 meters per second at a height of 500 meters above the observer. Calculate the frequency of sound reaching the observer when the plane is seen to be directly overhead. So we have a scenario where we have our observer right here, and we have the plane directly flying overhead like this. That's our plane, guys. So the plane is 500 meters above the observer. Now the idea for this equation is that sound travels relatively slow compared to things such as light. So we cannot assume that sound travels basically instantaneously, just like we can assume light travels instantaneously. So the sound that the observer hears when the plane is directly overhead would have been emitted when the plane is back here. Right? So the sound that the observer hears when the plane is directly overhead is the sound that the plane emitted from way back here. And so what you can see is that we have created a sort of right angle triangle with a right angle over there. So if we draw that more neatly, we have our 500 meters. However, we do not know this and this distance. What we do know is that the plane is traveling at 113 meters per second, and the speed of sound is 340 meters per second. We also know that velocity is distance over time, and therefore distance is equal to velocity times time. Now, based on this scenario right here, we can say that the time taken for the plane to travel this distance, let's call that time t, is the exact same time taken for the sound to travel this distance to the observer, which is the same t. So as distance is velocity times time, we can say that this distance right here is 113t, and this distance is 340t. So using that, we can get this angle right here. The reason why we want that angle is that angle will allow us to take the component of the velocity, of the plane's velocity, that is pointing directly at the observer. So using our trig, we get theta is equal to cos 113t all over 340t. Now as we have t on the top and bottom, we can cancel those out. And we get our angle as 1.23 radians. So now if we take our component of the plane's velocity, which this is 113 meters per second, and we can take the upwards component like so, and the downwards component. Now this downwards component is the one that we're interested in, as this is the one that's going to be facing the observer. And this right here will be our theta. So this component right here is v cos theta, which is going to be 113 cos 1.23, which gives us a velocity component of 37.78 meters per second. Now this value here is going to be our Vs in our Doppler equation, and we know our Doppler equation is as so. Now plugging in our numbers, and this gives us a perceived frequency of 1125 Hertz. There we go. A plane flies with a constant vertical lift force so that it maintains a uniform height. It has an unloaded mass of 3,000 kgs and is carrying a cargo pod of 1,000 kgs. When it is overhead, it drops its cargo pod but maintains the same constant lift force. Calculate the vertical separation between the pod and the plane when the pod has been falling for 1.5 seconds. Okay, so in this scenario, we have our plane. All right. And that plane is carrying a cargo of 1,000 kgs. And so afterwards, the plane then drops that cargo. So the cargo is now falling, and because initially the plane is maintaining a constant uniform height, its lift force, Fl, is going to be equal to its weight force. So there's no net force, and therefore there's no acceleration, and so it stays at a constant height. However, when the cargo is dropped, it maintains the same lift force, so the lift force is going to be the same as before. However, because the cargo is now dropped, its weight will decrease, its mass will decrease, and therefore the weight force will go down, it will decrease. And so therefore, the plane will have an excess lift force, and therefore as there is now a net force, the plane will accelerate upwards. So the cargo is falling down, but also the plane is moving up. And so we need to take the distances that both the plane travels and the cargo travels in 1.5 seconds into consideration for this question, as we are measuring the separation between the cargo pod and the plane. So the weight force of the plane and the cargo pod in the beginning is going to equal to the 3,000 kgs of the plane plus the 1,000 kgs of the cargo pod times 9.81, which is g. And this is going to give us a force of 39,240 newtons. And as discussed previously, this weight force is going to be the same as the lift force. Now afterwards, the weight force is just going to be the cargo pod. So that's just 3,000, and then still times 9.81, and that's going to give us a force of 29,430 newtons. Now from this, we can calculate the net lift force by taking the after minus the before. So the net lift force is going to be equal to the force before minus the force after, and that gives us a net force of 9,810 newtons. That value is the net lift force of the plane after the cargo has been dropped. So now, due to F is equal to ma, and therefore A is equal to F over m, we can calculate the acceleration that the plane experiences after the cargo has been dropped. And so we have our 9810 divided by the mass, which is just the mass of the plane, so that's 3,000 kgs, and we get an acceleration of 3.27 meters per second. Okay, so to calculate the distance, we can use the kinematic VIT plus half AT squared. As VI initially is equal to 0, this cancels out, and we get our distance is equal to half AT squared. Now we can get the distance of the plane, and that's going to equal to half our acceleration is this right here, and our t is our 1.5 seconds, and that gives us a distance of 3.68 meters. Now we can do the same thing for our cargo, the distance of the cargo, and that is still equal to half times the acceleration. Now the acceleration experienced by the cargo is just the acceleration due to gravity, and so that's 9.81, again times the time, which is the same, 1.5 seconds squared, and the distance traveled by the cargo is 11.04 meters. And so the total separation is equal to 11.04 plus 3.68, which gives us a total separation of 14.7 meters. Okay, question 2. A mass of 1 kg is dropped 2 meters onto a sticky platform of mass 2 kgs. The platform sits on a spring with a spring constant of 100 newtons per meter. By using approximate conversion laws, show that during the collision between the mass and the platform, 2/3 of the gravitational potential energy lost by the mass is converted into heat. State any assumptions made. Okay, so we are going to assume that all the gravitational potential energy is going to be converted to EK for the mass that is being dropped. So that means the EP is equal to mgh, and therefore 1 times 9.81 times 2 meters is equal to 19.62 joules. And therefore our EK is equal to 19.62 joules. So now, as we know the kinetic energy of M1 is going to be 19.62 joules, we can use the kinetic energy formula, half mv squared, to get the velocity of the 1 kg mass. So as EK is equal to half m1 v1 squared, labeling 1 for the 1 kg mass, that means 19.62 is equal to half m1, which has a mass of 1 kg, times v1 squared, which is what we're trying to find. So that means 2 times 19.62 all over 1 kg, and everything being square rooted, we get v1. And that means v1 is equal to the square root of 39.24. So using another conservation law, the conservation of momentum, the momentum initially is going to equal the momentum finally. So the momentum initially is just going to be m1v1, as that is the only thing that's moving. The 2 kg mass isn't currently moving, so that has no velocity and therefore no momentum. However, the momentum finally is going to be m1 plus m2 times the velocity afterwards, which we can call v2. Now, as m1 is equal to 1 kg and m2 is equal to 2 kgs, m2 is equal to 2m1. And so therefore we can rewrite the momentum finally as m1 plus 2m1 times v2. And therefore the momentum finally is equal to 3m1 v2. Therefore, m1 v1 is equal to 3m1 v2. Cancelling m1 on both sides, we get v1 is equal to 3v2, and therefore v1 all over 3 is equal to v2. Plugging in our value of v1, 39.24 all over 3 is equal to v2. So now that we have the velocity after m1 and m2 have collided, which is our v2, we can get the kinetic energy after m1 and m2 has collided. So that's our half mv squared again. So plugging in our numbers, we get half our mass is both m1 and m2, so that's 1 plus 2, and that's 3 kgs, times our v2, which is our 39.24 all over 3 squared. And that gives us a kinetic energy of 6.54 joules. So as you can see, we initially started with 19.62 joules, and we have ended with 6.54 joules. So the question has asked, show that 2/3 of the energy has been lost to heat, and we can prove this by going 6.54 divided by 19.62, and that is equal to 1/3. So that means 1/3 of the total energy initially is then converted into kinetic energy, and therefore 2/3 of the energy must go to heat. Show that the maximum amount of additional compression that occurs in the spring is 0.73 meters. Okay, so if we have our spring, like so, if we place a 2 kg mass on this, you can imagine that the spring is going to be compressed slightly. So that's our 2 kg mass. This is not the compression that we're looking for. We're looking for the additional compression. So the additional compression is when we have that 1 kg mass on top of that 2 kg mass, and it's going to compress even further. However, we still need to take the initial compression of the 2 kg mass into consideration. So let's first do that. We know that F is equal to kx, and therefore x is equal to F over k, where our force in this case is our weight force of the 2 kg mass, and so that's 2 times 9.81, and therefore 2 times 9.81 all over the spring constant of the spring, which is stated above here, which is 100, and that gives us a compression of 0.1962 meters. So just by the 2 kg mass being on the spring, it is compressed by 0.962 meters. However, when we put that 1 kg mass on, it is going to be compressed further, and this additional compression is what we're looking for, and we can call that delta x, right? So the 2 kg mass might compress the spring down to here, but with the 1 kg mass, it might compress it down to here. And so this distance right here is our delta x that we're looking for. And this is our initial compression. So as we know that the potential energy in a spring is equal to half kx squared, and therefore the energy finally is equal to half kx plus delta x squared. Now this x is our x up here, which is our 0.962, which is our initial compression, and the delta x, as stated before, is the additional compression. So this is afterwards. This is the total potential energy after everything has settled down and there's only potential energy in the spring, no more movement. And so that must be equal to the kinetic energy. So when the 1 kg mass is dropped onto the 2 kg mass, there is going to be movement, of course, and therefore there's going to be kinetic energy involved. And this is in addition to the potential energy in the spring before the 1 kg mass has been dropped. So when it was just a 2 kg mass, that's why we have only x squared here. And that is also added to mg delta h. So what this is before the 1 kg mass has been dropped and it was just a 2 kg mass, the spring would have been not as compressed, and therefore the 2 kg mass would have been standing higher. But when the 1 kg mass drops, it's going to push the 2 kg mass slightly further down, and that's going to cause a decrease in gravitational potential energy. So that means before, which is this side, there is going to be more gravitational potential energy, which is this right here. So now expanding this out right here, we get half k x squared plus 2x delta x plus delta x squared. And that's equal to half mv squared plus half kx squared plus mg delta x. Now we can plug in our numbers and we get half k, which is half of 100, so that's just 50. X, which is our 0.1962, plus 2x, which is this times 2, which is 0.3924 delta x plus delta x squared. And that's equal to half m, again, mass 1 plus mass 2, which is 3 kgs, times the velocity squared, which is what we found before, which is 39.24 all over 3 squared, plus half k, again, that's just 50, times x squared, which is 0.1962 squared, plus m, again, 3 kgs, times g, which is 9.81, times delta x. So solving this, we get 1.924722 plus 19.62 delta x plus 50 delta x squared. And that's equal to 6.54 plus 1.924722 plus 29.43 delta x. And so we can cancel these values on both sides because they're the same number. And so we get 19.62 delta x plus 50 delta x squared is equal to 6.54 plus 29.43 delta x. And now we can move everything onto the left-hand side to make the right-hand side equal 0. And so we get 50 delta x squared minus 9.81 delta x minus 6.54. And as you can see, this is a quadratic equation. And so our quadratic formula is equal to negative b plus or minus b squared minus 4ac all over 2a, where this is our a value, this is our b value, and this is our c value. So delta x is equal to negative b, where negative 9.81 is just equal to 9.81, because negative 1 times anything negative is going to be the positive version. So we get 9.81 plus or minus b squared, which is negative 9.81 squared, minus 4ac, so 4 times 50, and our c value is negative 6.54, and that's all over 2a, which again, a is 50. And so solving this gives us a delta x of 0.4728 meters. And that is the value that we are trying to find. There we go. Calculate the amplitude of the resulting vibrations. So the amplitude is going to be equal to the compressed distance minus the equilibrium. So our new equilibrium is x is equal to F over k, where our force is still the weight force. However, our mass is now 3 kgs, because now we have the 1 kg mass plus the 2 kg mass, and so that is 3 times 9.81. And that is all over our k value, which is still 100 newtons per meter, and that gives us a new equilibrium position of 0.2943 meters. Now our total compression is going to be equal to the additional compression plus the initial compression, so that's 0.4728 plus 0.1962, and that's equal to 0.669 meters. And so using this equation that we formed above, our amplitude is going to be equal to 0.669 minus 0.2943, and that gives us an amplitude of 0.3747 meters. Show that the total energy at the bottom of the motion is equal to the total energy at the top of the motion. So at the bottom, all the energy is in the potential energy of the spring, which in a previous question we found that that is equal to half kx plus delta x squared. So plugging that in, we get half times our K value, which again is 100, plus our X plus delta X, which we found was just 0.669. And that's all squared. And that gives us a potential energy of 22.38 joules. Now at the top we have our mgh plus our half k, and our x value at this point is our amplitude minus our equilibrium position, our 3 kg mass, our g is our 9.81, and our h is our delta h, and the change in height is twice our amplitude, which is 2 times 0.3749 plus our half k, which is again is 100, times our amplitude, which is 0.3749, minus our equilibrium, which is 0.2943 squared, and that gives us a energy of 22.38 joules. Therefore, it is the same at the top and at the bottom. Okay, question 3. Monochromatic light of wavelength 375 nanometers is incident on a metal surface. A potential difference of 1.31 volts is required to cut off the flow of photoelectrons. Calculate the work function of the metal. So we know that the energy of the photoelectrons is equal to HF minus the work function of the metal. Therefore, rearranging for our work function, we get the work function is equal to HF minus the energy of the photoelectrons. Now we can calculate the energy of the photoelectrons as we are given the voltage required to cut off the flow. That means that the electrons have 1.31 electron volts of energy. Therefore, we can times that number by the charge of an electron and we get the energy that the electrons have in joules. So the energy of the electrons is 1.31 times 1.6 times 10 to the negative 19, which is the charge of an electron, and we get 2.096 times 10 to the negative 19 joules of energy. And in order to get the frequency of the photons that are hitting the metal surface, we know that V is equal to F lambda, and therefore F is equal to our velocity over our wavelength. And the velocity of the wave is just the speed of light, so 3.00 times 10 to the 8, all over lambda, which is 375 times 10 to the negative 9, and that gives us a frequency of 8 times 10 to the 14 hertz. Therefore, our work function is equal to Planck's constant, which is 6.63 times 10 to the negative 34, times our frequency, which is 8 times 10 to the 14, minus our energy, which is 2.096 times 10 to the negative 19. And so that gives us a work function of 3.2 times 10 to the negative 19. There we go. And that is in joules as well. A 0.5 milliwatt laser of wavelength 581 nanometers is pointing at the moon. The laser beam spreads out at an angle of 1.65 times 10 to the negative 3 radians. Calculate the maximum number of photons arriving per second per square meter on the moon. Okay, so first things first, we can calculate the frequency of the light from the laser. We know our V is equal to F lambda, and therefore F is equal to V over lambda. Again, as this is light, velocity of the wave is just the speed of light, and so that's 3.00 times 10 to the 8 divided by our wavelength, which is 581 times 10 to the negative 9. And that gives us a frequency of 5.16 times 10 to the 14 hertz. So now that we have the frequency, we can find the energy of those photons. Using our E is equal to HF, and therefore E is equal to Planck's constant, which is 6.63 times 10 to the negative 34, times our frequency, which is 5.16 times 10 to the 14. And that gives us a energy of 3.42 times 10 to the negative 19 joules. We are given the power of the laser, and we know our power is equal to energy over time. And because we are looking for per second, our time is equal to 1. And therefore rearranging this equation for energy, we get E is equal to PT, and therefore 4.5 times 10 to the negative 4 watts times our 1 second gives us a energy of 4.5 times 10 to the negative 4 joules. Now dividing 4.5 times 10 to the negative 4 all over 3.42 times 10 to the negative 19, we get 1.31 times 10 to the 15. And this is the amount of photons per second. So just to recap, this energy right here is the energy of a single photon. And this energy right here is the energy emitted by the laser per second. So if we take the energy produced by the laser per second and we divide it by the energy of a single photon, we get the amount of photons per second. So if we picture our moon, right? This is our moon, we have our craters or whatever, and we have our laser. We can imagine that the light from this laser is going to be producing a cone-like shape as so. And this is our theta, which is the angle provided, right? So you can see that this distance right here is the distance from the Earth to the moon. We can call that distance L. And this distance right here is our diameter of the beam, and we can call that distance X. Now using this, we can use our small angle approximation, where we have our theta here, our L here, and our X here. And therefore, because of the small angle approximation, we can say that theta is equal to X over L. And in order to find the amount of photons that are hitting the moon per second, per square meter, we need to find this X value, right? Because that is going to be the distance that the photons are going to be covering, correct? So we can rearrange this equation for X, and we get X is equal to theta multiplied by our L. So therefore, X is equal to 1.65 times 10 to the negative 3 times our L, which is the distance from the Earth to the moon, which is this value right here, 3.8 times 10 to the 8, 3.8 times 10 to the 8, and that gives us a X value of 627,000 meters. As you can see, this is the diameter, but we want the radius, and so the radius is going to be X divided by 2, and that's 627,000 divided by 2, which gives us a radius value of 313,500 meters. There we go. And so area of a circle is equal to pi r squared, and therefore pi times our radius squared is equal to 3.09 times 10 to the 11 meters squared. And if we go back up here, we can see that we're trying to calculate the number of photons per second per square meter. And so that is the amount of photons per second per square meter. We have the amount of photons per second, that is this value right here. And we also have the area that the photons cover, which is this value right here. And so we can divide our photons per second by the area that it covers, and we get the amount of photons per second per square meter. So if we divide 1.31 times 10 to the 15 all over 3.09 times 10 to the 11, that gives us 4,257 photons per second per meter squared. A photon of frequency f1 and wavelength f1 is scattered by a stationary electron. The photon has a momentum given by that equation there. Due to the interaction, a photon of frequency f2 and wavelength lambda2 results. It travels in the opposite direction of the initial photon, and the electron gains energy of 4 kiloelectronvolts, with velocity v in the same direction as the incident photon. Calculate the value of lambda1. So this is another conservation of momentum and conservation of energy question. So starting off with our conservation of momentum, we know that the momentum initially must equal the momentum finally. The momentum initially is just h all over lambda1, and that's equal to the mass of the electron times its velocity minus h over lambda2. Now this comes from P is equal to mv, so standard stuff. And the reason why we're minusing h over lambda2 is because momentum is a vector, and this second photon travels in the opposite direction to the initial photon. So we are going from the initial photon's reference frame, so the initial photon is positive, and therefore the second photon must be negative. Now we can rearrange this equation for the second photon, and you'll see why we've done that later. And so we can leave that there for now, and let's move on to our conservation of energy. So our energy initially must equal to our energy finally. The energy of a photon is E is equal to HF, and therefore the energy initially is HF1, and that's equal to HF2 plus half MeV squared. So that's the kinetic energy of the electron, and these are the energies of the photon. As we know, V is equal to F lambda, and F is equal to V over our lambda, and velocity in this case is equal to c, the speed of light. And so F is equal to c over lambda. And therefore we can replace the frequencies with this equation right here. And we get hc over lambda 1 is equal to hc over lambda 2 plus half mev squared. Now we can divide both sides by c, and we get h over lambda 1 is equal to h over lambda 2 plus 1 over 2c mev squared. And now rearranging for h over lambda 2, h over lambda 2 is equal to h over lambda 1 minus 1 over 2c mev squared. So now that this equation here is equal to h over lambda 2, and so is this equation, we can make them equal to each other, like so. And we can gather our like terms by moving this onto this side right here. And we get mev is equal to 2h over lambda 1 minus 1 over 2c mev squared. Now we can times both sides by c to get rid of the c at the bottom. And we get mevc is equal to 2hc over lambda 1 minus half mev squared. Now moving this to this side right here, so we just have the term with lambda 1, and we get mevc plus half mev squared is equal to 2hc over lambda 1. And therefore, lambda 1 is equal to 2hc all over mevc plus half mev squared. So now that we have the equation for lambda 1, there's a few things we need to figure out. We know our c, because that's just the speed of light. Planck's constant is always a constant, so we have that as well. But what we don't have is the velocity of the electron and the kinetic energy of the electron. However, what we do know is that the electron gains energy of 4 keV, and therefore assuming no external forces, all this energy is going to go into kinetic energy, and therefore 4.00 times 10 to the 3 times the charge of an electron, 1.6 times 10 to the negative 19, is equal to 6.4 times 10 to the negative 16 joules. And that is the EK of the electron. Now that we have the kinetic energy of the electron, we can rearrange for velocity, and we can find the velocity of the electron. So again, we know our kinetic energy is half mv squared, and therefore our v is equal to square root 2ek all over m. And so our velocity is square root 2 times 6.4 times 10 to the negative 16 all over the mass of an electron, which is given up here as 9.11 times 10 to the negative 31. And that gives us a velocity of 3.75 times 10 to the 7 meters per second. Okay, so now we can plug these numbers into our lambda 1 equation, and we get lambda 1 is equal to 2 times Planck's constant times the speed of light, and that's all over the mass of electron, which we just found out, times the velocity of the electron, times the speed of light, and that's plus the kinetic energy of the electron. And that gives us a wavelength of 3.65 times 10 to the negative 11 meters. There we go. The number of electrons in 1 gram sample of hydrogen is approximately twice the number of electrons in 1 gram sample of any other light element. Explain why this is the case. Okay, so as a general rule, there are the same amount of protons and electrons in an atom, And also, and especially in lighter elements, the number of neutrons is also equal to the number of protons. However, when you get into heavier elements, this starts to vary. So the key idea here is that in hydrogen, hydrogen has no neutrons. And because protons and neutrons are much heavier than electrons, in 1 gram of hydrogen, almost its entire weight is protons. And as we said, there are the same amount of protons as electrons. And so if in a 1 gram sample of hydrogen, it's almost consisted of mostly protons, there's going to be the same amount of electrons. However, in other elements, they have neutrons. And protons and neutrons have very similar weight. And therefore, in other light elements, approximately half the weight is neutrons and half the weight is protons. And therefore, there is going to be much less electrons per gram. And so let's put that into words. Each electron within an element has its own proton. As H does not have any neutrons, only a proton, the 1 gram sample of hydrogen is almost entirely protons, as protons are much heavier than electrons. Thus, there is a high number of protons and therefore a high number of electrons per gram. However, other light elements have neutrons, thus half of their mass is neutrons and the other half is protons, because neutrons and protons are approximately the same weight. Thus, there are less protons per gram and therefore less electrons per gram. And this is approximately half the amount of electrons than hydrogen. Okay, question 4. The LCR circuit below is driven by an AC source of angular frequency omega. Show for the case where XL is greater than XC that tan phi is equal to that equation there, where phi is the phase angle between the source voltage and the current. So if we have our phasor diagram, where we have this is the middle, this is going to be our XL and this is our XC, and so this is going to be our resistance. This is our source voltage or our total impedance, and this is our phi. This dotted line right here is our omega L minus 1 over omega C, and therefore due to our tan relationship, where this is the opposite all over the adjacent, we can see that tan phi is equal to WL minus 1 over WC all over R. And there we have the equation that we're looking for. Explain using physical principles what happens to the angle phi when the capacitance increases. Okay, so if capacitance increases as XC is equal to 1 over omega C, if capacitance increases, therefore the XC must decrease. And therefore, if we look at our phasor over here, if this decreases, and therefore this line right here will be taller, and therefore the angle of phi would increase. So let's put that in words. As XC is inversely proportional to the capacitance, if capacitance increases, then XC will decrease. Thus the total impedance will increase, therefore voltage will lead current by even more. Thus the angle will increase. Another circuit is constructed as shown in the diagram. The source RMS voltage is 185 volts. When the switch is in position 1, the RMS current is 1.5 amps. The switch is now moved to the position shown in the diagram so that the resistance is included in the circuit. The source voltage lags the current by 30 degrees. Show that the resistance is 214 ohms. Okay, so now that the switch is in this position here, this is just a regular LCR circuit. Because this capacitor is just in no man's land, the current will just flow like so. So in the first question, we found that tan theta is equal to omega L minus 1 over omega C all over R. However, in that case, this is when voltage was leading current. However, in this case, voltage lags current. So this is what our phasor diagram will look like. If we have our phasor right here, we will have our XC and this is our XL. The voltage or the total impedance will lag the current by 30 degrees, like so. So before it was up here, but now it's down here. And so therefore, if we create our right angle triangle, this right here is XC minus XL, and therefore that's 1 over omega C minus omega L. And therefore we can replace this top part with 1 over omega C minus omega L. Now we can rearrange for resistance, and we get R is equal to 1 over omega C minus omega L all over tan theta. Now we know our theta is 30 degrees as it's given right there, but we do not know the value of our omega as we are not given a frequency, and we don't know our capacitance nor our inductance. So how do we find this value up top? Well, as stated previously, the switch was not in this position, and in fact it was connected like so. And therefore you can see that the resistance is effectively removed from the circuit, and therefore this is now just an LC circuit. And so the total resistance in this case is omega L plus 1 over omega C. So therefore, as we know the voltage and we know the current when it was in position 1, as V is equal to IZ, and therefore our Z is V over I, and again our total impedance is this right here. Therefore, total impedance is equal to 185 all over 1.5, and that gives us a total impedance value of 123.33 ohms. And therefore our resistance is equal to 123.33 all over tan 30 degrees, and therefore this gives us a resistance of 214 ohms, which is the value that we're trying to find. The switch is now moved to position 2, the source voltage now leads current by 15 degrees, show that the reactance of the circuit is given by the following expression. So now if the switch is in position 2, we now have 2 capacitors in play, and therefore as voltage now leads current by 15 degrees, omega L minus 1 over 2 omega C is now our equation, which is this part right here, so we're on the right track. And so if we have our trusty equation that we have used twice before, this one and this one right here, if we make that substitution, tan 15 is equal to omega L minus 1 over 2 omega C all over our resistance. We can rearrange for our tan 15 is equal to omega L minus 1 over 2 omega C. Now we found out in the previous question that our resistance is 214. Now 214 tan 15 degrees does indeed equal 57.2, and therefore 57.2 is equal to omega L minus 1 over 2 omega C. And there you have it. We have found our equation. Determine the values of the inductance and the capacitance. The angular frequency of the source voltage is 350 radians per second. So based on our previous questions, we know that omega L minus 1 over 2 omega C is equal to 57.2. And we also know that 1 over omega C minus omega L is equal to 123.33. And therefore, if we rearrange this for omega L, we get omega L is equal to 57.2 plus 1 over 2 omega C. So we can make that substitution into here, and we get 1 over omega C minus 57.2 plus 1 over 2 omega C. And that is all equal to 123.33. And so therefore, getting rid of this bracket, we get 1 over omega C minus 57.2 minus 1 over 2 omega C is equal to 123.33. And so plussing 57.2 on both sides, we get 1 over omega C minus 1 over 2 omega C is equal to 180.53. Now timesing the top and bottom of this fraction by 2 so we can get the same denominator on both fractions, we get 2 over 2 omega C minus 1 over 2 omega C, and that's equal to 180.53. And therefore 2 minus 1 all over 2 omega C is equal to 180.53. And therefore that is equal to 1 over 2 omega C is equal to 180.53. Okay, so now moving 2 omega C up here and moving 180.53 down here, we get 1 over 180.53 is equal to 2 omega C. Now dividing both sides by 2 omega and therefore rearranging for our capacitance, we get 1 over 180.53 divided by 2 omega, and we know our omega is our angular frequency, which is just 350, and this gives us a capacitance value of 7.91 times 10 to the negative 6 farads. There we go. Okay, so now that we know the value of our capacitance, we can find the value of our inductance by subbing into one of these two equations. Let's pick this one right here, where we have 1 over WC minus WL is equal to 123.33. Now we need to rearrange for our inductance. We can do this by moving this value onto this side and this value onto this side. And we get 1 over omega C minus 123.33 is equal to omega L. Now dividing both sides by our omega, we get 1 over omega C minus 123.33 all over our omega is equal to our inductance. Now subbing in our values, we get 1 all over our omega, which is 350, times our capacitance, which is 7.91 times 10 to the negative 6, minus 123.33, and that's all over our omega, which is 350. And that gives us an inductance value of 0.68 henries. There we go. Okay, question 5. A spring-loaded plunger launches a ball at speed v0 from the corner of a smooth flat board that is tilted by an angle phi, in order to make the ball hit a small target at the adjacent corner, at a distance d away, as shown in the diagram. The ball can be considered to be sliding without friction. Assuming the angle theta required to hit the target is known, show that the maximum distance up the board is given by that equation there. Okay, so for this question, I recommend that you get familiar with the range equation. I have a video on that on my channel. I think it's in the deriving formula video. And also for this equation, we need a solid understanding about projectile motion. In projectile motion, we understand that the vertical motion is dictated by kinematics, and the horizontal motion is dictated by our v is distance over time. So for this question, this launch angle is just standard level 2, where we have a projectile going at v0, and we have an angle which is theta to the ground, and therefore the horizontal velocity is v0 cos theta, and the vertical velocity is v0 sine theta. However, the part that makes this question slightly tricky and a scholarship question is this phi right here. What this does is obviously make the plane slightly angled, and therefore our ball will be sliding down a slope, and therefore as g acts straight down, the component of g that is acting down the slope will be g sine theta. And I've also made a video why g is g sine theta down an inclined plane, if you are wondering why that is the case. So we are looking for the maximum distance up the slope, and so our velocity in the y direction is going to be v0 sine theta, as we have discussed right here. Also, our acceleration is going to be negative g, as g acts in the downwards direction, and that's going to be times by sine theta, as discussed over here. So for this question, we can use our kinematics vf squared is equal to vi squared plus 2ad. Now at the top of the motion, the ball will come to a complete stop for a brief moment, and therefore our vf is equal to 0. And therefore our equation is 0 is equal to vi squared, where our vi is our v0 sine theta, and that's all squared, plus our 2, and our g is negative g sine theta, so we can replace this plus with a minus. And that's times by our distance, where in this case our distance is our delta y. Now rearranging and bringing this term onto this side right here, we get 2g sine theta delta y is equal to v0 sine theta squared. And dividing by 2g sine theta, we get delta y is equal to v0 sine theta squared all over 2g sine theta. And we can bring this 2 out as a half, and we get delta y is equal to half v0 sine theta squared all over g sine theta. And as you can see, that is the equation that we are trying to find. Here we go. by considering the horizontal motion, show that the time reached to the target, delta t, is given by that equation there. So as we know in our kinematics, the horizontal motion is dictated by v is equal to distance over time, and therefore our time is going to be our distance over our velocity. Now our distance is just d, as seen here, and our velocity in the horizontal motion is our v cos theta, as discussed previously. And so we can just plug that in. Our delta t is equal to our d all over our v naught cos theta. And as you can see, that is the equation we are trying to find. Derive a relationship for the time to reach maximum height delta y. Express your answer in terms of v naught, theta, and phi. Okay, so for this we can use the kinematic Vf is equal to Vi plus At. Again, at the height of the motion, Vf is equal to 0, and therefore negative Vi is equal to At. Now, as discussed in the previous question, our A is going to be negative g sine theta, and our Vi is going to be V naught sine theta. And therefore, negative V naught sine theta is equal to negative g sine theta t. As we have negatives on both sides, we can just cancel them out, and we get V naught sine theta is equal to g sine theta t. Now we can divide both sides by g sine theta, and we get V naught sine theta all over g sine theta is equal to our time. And this is our final expression. Show that the angle theta at which the ball should be launched so the target is reached is that equation there. So over the previous two questions, we have established that our time is equal to distance over v naught cos theta, as well as our time is equal to v naught sine theta all over g sine phi. And therefore, as these two expressions both equal to time, we can make them equal to each other. So we get d over v naught cos theta is equal to v naught sine theta all over g sine phi. Now cross multiplying, we get dg sine phi is equal to v naught sine theta times v naught cos theta. Now using the trig identity that is given above right here, we can simplify this side of the expression as v naught squared sine 2 theta, and that is still equal to dg sine phi. And so dividing both sides by v naught squared, we get dg sine phi all over v naught squared is equal to sine 2 theta. Now dividing both sides by 2, we get dg sine phi all over 2v naught squared. Now we can bring out that 2 as a half, and that's equal to sine theta. And therefore our theta is equal to half inverse sine of dg sine phi all over v naught squared. And that is the final expression that we are trying to find. Sweet as. Now consider the case where the ball rolls without slipping. If the ball with mass m and radius r has a rotational inertia of 2 over 5 mr squared, and assuming again that theta is known, show by conservation of energy that delta y is equal to that equation there. So right off the bat, if we are considering a case where the ball is not slipping, there is going to be rotational kinetic energy, and so we are considering the linear kinetic energy plus the rotational kinetic energy. We know linear kinetic energy is equal to half mv squared, and our rotational kinetic energy is equal to half I omega squared, where our omega is our velocity over our radius, and therefore omega squared is our velocity squared all over our radius squared. We also know that I is equal to 2 over 5 mr squared, as given up here. So now if we look at our conservation of energy, at the bottom, we have kinetic energy and rotational kinetic energy, but no gravitational potential energy. And so we have half mv naught squared plus half I omega squared. Now plugging in our I and our omega, we get half mv naught squared plus half 2 over 5 mr squared v naught squared all over r squared. Now, as you can see, the two r squares cancel out, and therefore we get half mv0 squared plus half 2 over 5 mv0 squared. And now, as you can see, we have two separate expressions with the same variables, and so we can add them together, and that equals 7 over 10 mv0 squared. Okay, so now at the top of the motion, our velocity in the y direction is equal to 0, as stated previously. However, we still have velocity in the x direction, and therefore, as we still have both rotational and linear kinetic energy, we can just use this expression right here, which is our rotational and linear kinetic energy combined. And so we get 7 over 10 mv0 squared. However, our v0 in this case is equal to v0 cos theta. As stated before, our velocity in the y direction is equal to 0. And so that is v0 cos theta squared. And at the top, we also have gravitational potential energy, which is equal to mgh. As stated previously, our g is equal to g sine phi, and our h in this case is our delta y. And therefore, our gravitational potential energy is mg sine phi delta y. Okay, so now that we have the two expressions for energy at the bottom and energy at the top, we know that due to conservation of energy, the energy at the bottom is equal to the energy at the top. And so 7 over 10 mv0 squared is equal to 7 over 10 mv0 cos theta squared plus mg sine phi delta y. Now we can cancel all the masses, and we get 7 over 10 v0 squared is equal to 7 over 10 v0 cos theta squared plus g sine phi delta y. Now, gathering our like terms, we can move this expression onto this side right here, and we get 7 over 10 v0 squared minus 7 over 10 v0 cos theta squared, and that's equal to g sine phi delta y. Now, simplifying this side of the expression, we can take 7 over 10 v0 squared out as a common factor. We get 7 over 10 v0 squared, 1 minus cos squared theta. And that is again equal to g sine phi delta y. Now, due to this trig identity right here, we know that sine squared theta plus cos squared theta is equal to 1. And therefore, sine squared theta is equal to 1 minus cos squared theta. As you can see, we have that expression right here, so we can make that substitution. 7 over 10 v0 squared times sine squared theta is equal to g sine phi delta y. Now dividing both sides by g sine phi, and we get 7 over 10 v0 squared sine squared theta all over g sine phi is equal to delta y. Now we can simplify this by taking out these two squares out here, and we get 7 over 10 v0 sine theta squared all over g sine phi, and that's equal to delta y. As you can see, that is the expression that we are trying to find. Consider the situation where angle phi is equal to 0 degrees. Explain the result produced. Due to the equation derived from the previous question, as phi tends towards 0, delta y will tend towards infinity. Thus, due to Newton's first law, the ball will move in a straight line. Comparing the answers for AI and C, explain why the answer for C is larger. In C, rotational kinetic energy is also included. Therefore, in order for the ball to travel the same range, more energy needs to be inputted. So we can write that in. In C, the ball was also given rotational kinetic energy, therefore the ball required more energy to travel the same range. Okay, there we go, and we're done.